Okay, so I welcome you all, and today we are going to talk about variational principle. Of course, variational principle has its touch from classical physics as well, but we do extensively use variational principle in quantum mechanics because most of the problems in quantum systems are very complicated problems. You cannot directly solve these problems. You cannot directly have solution of these problems. And if you rightly remember, before variational principle, we extensively discussed perturbation theory. And perturbation was a means to basically understand a system in which you were trying to disturb a system with a small magnitude of the perturbation. And, and you calculated that perturbation in the framework of the known Hamiltonian. You knew exactly how to solve that problem. But now we are in a domain where we don't know anything about the system. You have not a known story of your system. And this comes up in the framework of variational methods. So we make use of variational principle to understand, to get the approximate results of a system. Now again, if we go back to our curiosity kind of story, I want to share another imaginative story, and the hero of this story is Isaac Newton. If you rightly remember, it was nearly 1665 when there was plague in Britain, and it was a dangerous disease that was spreading all around, and people were dying. And it was the time when Isaac Newton, he didn't turn up. He was inside his house. He was inside his cabin, where he was curious. He was curious about the problems. And this time, his curiosity was not about the fall of an apple that led him to the universal law of gravitation. It was not about discovering the calculus, which in modern times, even the kids from America, they find it difficult when they are in higher secondary grades. But this time, the man looked at the same flame of a candle. You have a candle, and a flame is buzzing out of this candle. Now the point is, do we actually come up with the research when we suppose I have something and I intend to search for something? We believe that the greatest things in the science have not happened this way. The greatest things have happened only by looking at the problem. How keenly you are looking, how keen you are about looking a problem. Now, what am I trying to express here is that this candle has a flame, and flame has a shadow. And the man sitting inside his home, not allowed to come out of his house because plague is outside, and he is looking at the shadow of the flame of this candle. And when he looks keenly, see, it has happened accidentally. He did not plan a review of literature for it. He did not write down that I'm going to solve this problem. It was his curiosity. He looked at the shadow of the flame. And what he found? He found at the edges of that shadow, he could not find the complete darkness. He found a mixture kind of light on the edges of the shadow, You are in a dark room, the plague is outside, a candle is lit in your room, and you are looking at the shadow of the flame of this candle. And what clicks the man? It clicks. Why there is a mixture kind of shadow at the edges of this flame? So you see, there is a lot of curiosity. Everybody has a candle. Everybody lights it. They use it. But this man is focusing the dynamics of the shadow that's produced by the flame of this candle. So this hits his mind. It clicks him. And what he does, he goes for a hole. He develops a pinhole. It was a time, till this time, people completely believed that light is white. It's a pure light. It was the complete understanding of the people of that time. And what he does, he doubts that mixing. He doubts the shadow. And what he does, he makes a hole. And he manufactures a shutter on it so that he can close it, he can open it. Then in front of that hole, he puts a prism. And when he puts a prism, he allows the light to fall. He allows the light to cross the hole. And what he finds? He finds the splitting of white light. It's not an ordinary outcome. It's not an ordinary thing that has been discovered by this man. All of your astronomy from A to Z is dependent on this spectrum of light. This is the only information that we are receiving on the planet. Because light is showing different colors. And different colors bend at different angles. So each color has its own characteristic wavelength. It has its own characteristic angle at which it bends out of the prism. And what we are doing in modern times in astronomy, we are receiving the electromagnetic spectrum. And it's this electromagnetic spectrum that's giving us the information about the universe. Is there any other way? For that, you are using very sophisticated telescopes. You have telescopes on the surface of the planet. You have telescopes orbiting the Earth in the form of James Webb Telescope. But see, this small result, it seems extremely small, but it has given birth to all modern sciences that you have. And it has given you an edge to realize that what cosmos is, what universe is. You have a complete measurement chart. You can say this is the observable universe. Because only the light that you can receive from, there may be universe beyond the observable universe. But we are reporting only that what we receive. Right? So it's a small flicker basically. It's a small kick. And concentrating that click can lead to a very, very fundamental reality that we don't understand. So our target is variational principle. Let me introduce you with this. What we have, we would not include any mathematics here. Then I will start with the mathematical argument. So it has very, very strong implications in quantum mechanics because it's a principle that is giving you an approximate energy of the ground state of the system. And you don't know anything about the ground state energy of that system. You can use this variational principle. It's a very powerful method in quantum mechanics. And of course, everything in quantum mechanics we have approximate, apart from some idealistic problems like particle in a box. So, so for approximating the ground state energy of the system, you can approximately calculate the ground state energy. It provides a way to estimate energies when exact solutions are not possible. Exact solutions. So this makes a difference between the perturbation and the variational principle. In perturbation, you solve your problem in the framework of what is solvable, right? But that's not the case in case of variational principle. It's something, you are shooting something without knowing anything about the system. So this method originates from classical mechanics, I told you, and was adapted in quantum mechanics by the pioneers like Schrödinger and Heisenberg. Okay, and it became a cornerstone in computational quantum physics. Most of the times, when you do the computational physics, variational principle is a very basis. So what is the basic idea now here? So you have a system, you don't know anything about the system. So you don't know anything about the system. What you do to solve that system? You guess a trial wave function. You choose a trial wave function. And then you calculate the expectation value of this wave function. The expectation value of the Hamiltonian will always be greater than or equal to the true ground state energy of that system. So what you do, you choose a trial wave function. Then you calculate the expectation value. You have a Hamiltonian of that system. You calculate that using expectation value. And what it does basically is this allows us to approach the exact value by improving our guess. So that means you are guessing a wave function. You are guessing a trial wave function. And your guess cannot be always right. Okay? So you choose this guess, and if your solution is close to the ground state energy of the system, close or greater than that of the ground state energy of your system, then you are on the right track. So what you calculate this energy. You calculate this energy using the trial wave function. The trial wave function that you have introduced. You calculate the Hamiltonian. Once you calculate the Hamiltonian, if this E comes greater or equal to the ground state energy, then you are on the right track. And if you get it less than that of the ground state energy, you're on the wrong track. So variational principle is very important here in how pure, how accurate your guess is. That leads you to the approximate close result of the problem that you are discussing. So what you have here, basically, you have an inequality, okay? So the energy that you are calculating, it's either equal to the ground state energy or it's greater than that of the ground state energy. So now if you look at this graph, can you see it? You have a graph here, okay? You have energy versus trial parameters. So now if you look at the dotted line, this dotted line is an indicator of the true ground state energy. And now you see, you are choosing a trial function that's given to this point. You are choosing another trial function that's given to this point. So these 2 points are very far. Are you getting my point? So they are bad trial wave functions you have chosen for your system. And then you have a trial function that's exactly matching to the ground state energy. And something that's close to this ground state energy. They are both acceptable, okay, depending on the type of the problem. But it should not be far as like these points. It should not be like this. So this graph can tell you exactly that where you are guessing a trial wave function is close to the problem that you are discussing. Are you getting me? Okay? You get this graph? Okay. So, now point is why it works. The principle is based on the fact that the true ground state minimizes the expectation value of the Hamiltonian. Okay, the true one. See, you have hydrogen atom with one electron. Now, if I talk about the helium atom with how many electrons? 2 electrons. Okay, helium. Now the problem is complicated. Okay, so what you can do, you can come up with a trial wave function. If your trial wave function is close enough, okay, your ground state energy will be greater or equal to, sorry, the energy that you will calculate using that trial wave function will lead us to what? The true energy of that system, the energy that's close to the true energy of that system. So any deviation from the true wave function increases the energy. So you will see that there will be more increase in the ground state energy of the system if the trial wave function you have chosen is not an accurate, is not something that's very close to define your system. Again, choosing a trial wave function. So what we have, the success of the method depends on the choice. So it's not like that you will do anything, okay? So you have to choose 1 out of 100. You have to choose 1 out of 10. So it must have a physical logic in your mind that what you are going to choose for it. Or you getting my point? You're not going to choose a door for the cabin which is very, very big so that it will not fit to your cabin. So again, you have to choose here. You have to use the skill so that your results are very close to the reality. It should incorporate the symmetry of your problem. The trial wave function that you are choosing, you cannot choose any damn thing. It must be symmetry. It should symmetrize. I will not make a car kind of object for the door because I see the cabin and the cabin demands a rectangular thing. Suppose this cabin is rectangular. I will not choose a circular door for it. So what is important here is that it should incorporate the symmetry and the boundary conditions of the system. Okay? To which extent your system is bound and what are the bounding natures. So you can see here, suppose I choose this graph, you can see it has a complete resemblance with the Gaussian distribution function. Now, most of the nature that we have behaves like this. Now, if the y-axis is the amplitude and the x-axis is the position, now you can see you have the dotted lines. These dotted lines are coming out of the trial wave function that you have chosen. Okay? And you have the solid line. The solid line is the result of the true value. And you can see the deviation. And you can see that there is a larger deviation at the core. But when you go to the edges, you see the two things are overlapping. And you see the peak is overlapping. So in this case, the trial wave function is a very good approximation because the results that you are obtaining for your problem, they are very much close to the true value of your system. Is this clear? Clear? Okay. So it is an approximation. It has applications to approximate the energies of atoms, molecules, and solids. Come on. This is what makes it very strong. You can exactly solve the problem of hydrogen atom, but you cannot exactly solve the problem of hydrogen molecule. Can you do that? No, you cannot do that. Even if you try to do it analytically, you will come up with the trivial solutions, and for that you may have to use a dozen of 200-page copies. No, that's not the case. Variational principle, it paves the way. It gives us the measures of energies of atoms, molecules, and even solids. So you can see the credibility of this method. It's a very strong tool in condensed matter physics. It's a very strong tool in molecules, where you have chemical kind of things. Okay? Essential in fields like quantum chemistry and nuclear physics. Your nuclear physics, where you always approximate to a system, okay? It has very strong applications in those frameworks. Now, talking about the hydrogen atom, suppose. So a simple example is approximating the hydrogen atom in ground state energy using a trial wave function. Okay? So with an adjustable parameter. So now you have a trial wave function. You would like to incorporate in your trial wave function a constant, but that constant has to be adjustable. Suppose I call something psi equal e to the power of alpha r. So alpha is what? Alpha is an adjustable constant. You would like to adjust it. You understand that the symmetry of the problem is like, say for example, a e to the power of alpha r. But now you have to work on the alpha so that the result is very close to the ground state. Is this clear? So by minimizing the calculated energy, we get the close to the exact value. So how do we minimize? Suppose I calculated the energy using variational principle. How do I minimize? Because I can calculate this alpha by minimizing the system. How do we minimize the system? Any idea about the maxima and minima? How do you differentiate mathematically? Yeah. Assume that you have a maxima or a minima. Yeah, you take its derivative and you say the derivative of that physical quantity is equal to 0. So using that condition, you can calculate these values. It has role in computational methods. It's the foundation for many numerical methods like Hartree-Fock density functional theory, what we generally call as DFT. These are very powerful mathematical tools. So variational principle has a role in both of these models that we use in computations. Strength, it's simple in concept. It's very simple. You choose a wave function. You choose a trial wave function. Works even without full knowledge of the system. You don't know anything about the system, but still it works and provides an upper bound to the ground state energy. At least it gives you the upper bound of the ground state energy of the system that you're discussing. Limitations, obviously it must have limitations. Its accuracy depends heavily on the trial function. As I said, as we discussed about it depends on the trial wave function, the choice, what you choose for your system. And you cannot directly find the excited states without the modifications. You have a system going into the excitations. You cannot use variational principle to calculate the excited systems. What do you mean by excited system? You have hydrogen atom in ground state. Okay, your electron in the first orbit can be excited to the next. Okay, now it fails actually to give you the excited states, but you can make some minor modifications where you can still have an information about the higher energy states of that system. So methods like Rayleigh-Ghay's procedures, they extend the variational principle to more complex problems. These are the methods, the numerical methods that we can use incorporating variational principle and can solve the complex problems. So this principle is a versatile and intuitive tool for tackling quantum systems, where exact solutions are not possible. You see, not possible. You cannot exactly solve these problems, right? So what does it mean? What does it mean mathematically? What am I trying to say? Is it the lost? Yeah. What does it mean? It means It means variational principle. What do you do basically is you choose a trial wave function, say psi. You choose it. And you operate this trial wave function on the Hamiltonian of that unknown system. So you have a Hamiltonian operator. Okay? You have come up with a trial wave function, say ket of psi, okay? And you operate this trial wave function on this Hamiltonian. What does the operation mean here? It means you calculate the expectation value. And the expectation, so E trial, what is expectation? That is psi, h cap, and psi. This is divided by psi and psi. So the trial wave function that you have chosen, you normalize that wave function, right? When you normalize that, the denominator of this will be equal to 1. Okay? So what you calculate ET is the expectation of psi, h, and psi. And if the energy that you have calculated, if this E trial comes out to be, if it comes out to be greater, the E trial, if it comes out to be greater or equal to the ground state energy of that system, then you are on the right track. Okay? So the trial wave function you have assumed, it works for your problem. Otherwise, you have to change it. Otherwise means if this ET is less than the ground state energy of that system. Is this clear? Okay, any questions you can ask me? Yes? Come on. Come on. So in the next class, we'll be solving some of the problems based on variational principle. Okay?